Okay, so welcome to section 3.3. In section 3.3, we're going to take a look at the product, quotient, and higher order derivatives. So product and quotient, those are rules for taking derivatives. And then we'll take a look at some higher order derivatives. Remember how I mentioned before that we were taking first derivatives, and that kind of implied that there was going to be more? So first derivatives, second derivatives, third derivatives. All right, so the objectives for this section, very straightforward. Find the derivative function using a product rule. Find the derivative of a function using the quotient rule. Find the derivative of the other trigonometric functions, because if you think back to last section, all we had was derivative rules for sine x and cosine x, and that's only 2 out of 6, so we need more. And then find a higher order derivative. That means find a second derivative or a third derivative. All right, we're going to start with the product rule. So some more differentiation rules. Remember, our goal with the derivative rules, the differentiation rules, our goal is to never have to use the limit definition again. Now, up till now, we've got rules for certain things, but what we don't have a rule for is what to do when we have two functions, an f function and a g function. So two functions that are differentiable that are being multiplied together. Now you might just say, well, why not just multiply it out? What we're talking about is something like this. Suppose that I gave you the function y equals x squared times sine x. Okay, so there's a function f, and I know how to take the derivative of x squared. I can do that. There's a function g. I know how to take the derivative of sine. I can do that. But how do I take the derivative of two things that are being multiplied together? I don't have a rule for sine times x squared, so I can't do that yet. Okay? All right, but now we do have a rule. It's called the product rule. And the product rule simply states that if you are asked to take the derivative of an f times a g, that the derivative is f times g prime plus g times f prime. Each function multiplied by the other function's derivative added together. So f times g prime and g times f prime. Now, because addition is commutative, it really doesn't matter that you do it in this order. It doesn't have to be fg prime plus gf prime, but it does have to be each function times the other's derivative. Okay? All right, so let's take a look. Now we'll start out with some problems here. Now you might be looking at these and saying, hey, couldn't you just multiply that out? And the answer to that question is yes. I could just multiply this out, or I could just multiply that out. And that would get the job done. But what I want to do is I want to just take a look at an example of this product rule. And I wanted to keep things relatively uncomplicated. I didn't want to have to introduce ugly equations right away. All right, so let's look at this one. Here we have h of x. H of x is defined to be something times something else. All right, now before I go any further, I want to introduce a different notation for the product rule that's going to make talking about these functions easier. While this is not bad notation, right, simply using f of x and g of x every single time is going to make things complicated when we have problems like this. Because I can't look at this and I can't call this first one f because the name of the entire function is f. So I want to introduce you to some notation that is much more common when the mathematics gets more complicated. And it would be this, right? Let's say that u is going to be the f of x over there. And let's say that v is going to be the g of x over in that definition. Then the derivative with respect to x of u times v is going to be u times v prime plus v times u prime. And the reason I like this definition or this notation better is now I can just come over here to this problem and say, well, call this one u, call this one v, come over to this problem and say, call this one u, call this one v, and there won't be any confusion about, wait, which f are you talking about? Are you talking about the entire function f, or are you just talking about the first piece f? Okay, which is why I prefer that notation. I understand that not every instructor or not every author of every textbook is going to use it, but it is it can get confusing when you have two different things in the same equation and you're trying to call each of them f. Okay? All right, so back to the work. I'm over here on the left working on this problem. My job is to take the derivative of h of x. H of x is two things being multiplied together, u times v. Whenever I see two things being multiplied together, I need to use the product rule. Now, the first few times I use the product rule, I'm going to go step by step by step. And so I'm going to say that if u is equal to 3x minus 2x squared, then u prime, the derivative, is going to be 3 minus 4x. Okay? And if v is equal to 5 plus 4x, then v prime is just going to be 4. And now what I need to do is I need to take all of this and put it together using that definition. Right? So then h prime of x is going to be u times v prime plus v times u prime, or h prime of x is going to be 3x minus 2x squared, there's my u, multiplied by v prime, just a simple 4, plus v times u prime, so then v, 5 plus 4x, times u prime, which is 3 minus 4x. Okay? Now, unfortunately, even though it looks like it would be nice and it feels good just to leave it like that, we really shouldn't. What we really should do is we should multiply all that out, gather up like terms and all that business. So I'm going to go ahead and do that. Okay? So h prime of x, this first multiplication here, is going to give me 12x minus 8x squared. And the second one, the second product there, I have a binomial times a binomial, so I'm going to use FOIL to find that. First times first, 5 times 3 gives me 15. Outer is going to give me a negative 20x. Inner is going to give me a positive 12x. And last times last is going to be a negative 16x squared. Okay? Now I just need to combine like terms. Starting with my highest power, that's going to be my x squared. So there's negative 8 of them there, negative 16 of them there. Negative 8 and negative 16 is negative 24. So I have negative 24x squared. I'm going to cross them out so I don't miss anything. Now I'll do my x's. I've got 12x, 12x, and negative 20x. 12x and 12x is 24x. 24x less 20x is 4x. A positive 4x. I took care of that, and that. And then my constant term is just that 15. I only have one constant term. And there's my derivative. Right? Now, had I just gone ahead and multiplied it out to begin with, I would have ended up in the same place. And just to show that, I'm going to take this and drag it over here. If I had multiplied that out using FOIL, first times first is going to give me 15x. Outer is going to give me 12x squared. Inner is going to give me, what is that inner going to give me there? Negative 10x squared. And last times last is going to give me negative 8x cubed. Combining like terms, I've got 15x, I've got plus 2x squared, and I've got minus 8x cubed. Okay? That would be h, and then h prime. Derivative of 15x is 15. Derivative of 2x squared would be 4x. Derivative of negative 8x cubed is negative 24x squared. Same. Different order of terms, but same. So it would have been the same. So if you're wondering, why don't you just multiply it out? Well, for this problem, you could. Okay? So for this problem, product rule might be more than what you really need, but we're just learning it. So we want to learn it with something relatively easy so we don't have to spend a lot of time messing around with it. Right? All right. Let's take a look at our next example. Again, I have f of x is equal to u times v. So I'm going to define u. U is 6x plus 5. Then u prime would be 6. v is x cubed minus 2. So v prime is 3x squared. So then putting it all together, the formula tells me that the derivative of the function f is going to be u times v prime plus v times u prime. Okay. So that's going to be 6x plus 5 times 3x squared plus x cubed minus 2 times 6. That's my derivative. Okay. Now I have to do all the algebra. 3x squared times 6x is 18x cubed plus 3x squared times 5 is 15x squared plus 6x cubed minus 12. These are the only like terms I have, those two cubics. So then putting it all together, in the end, I get that the first derivative, f prime of x, is going to be 24x cubed plus 15x squared minus 12. And there is my derivative using the product rule. Okay. More examples. Okay. Here I have one where the product rule is absolutely necessary. There is no way around it. I cannot do this multiplication because I can't multiply an x squared times an e to the x. Those things don't play well together. So u is going to be x squared. So then u prime 2x. V is going to be e to the x. And so v prime, well, the derivative of e to the x is e to the x, my favorite derivative. So then putting it all together, the derivative of y with respect to x is going to be u times v prime plus v times u prime. U is x squared times v prime e to the x plus v e to the x times u prime, so times 2x. Okay. Cleaning that up a little bit, I get then that dy dx is e to the x times x squared plus 2x, or maybe if you prefer x e to the x times x plus 2. I don't know how much you want to factor these things. And there's our dy dx. Okay? So I'm taking derivatives using the product rule. I have another product here. I have a root of t multiplied by the binomial a plus bt. Okay? Going to use the product rule. So u is t to the 1/2. Remember, why did I rewrite it? Because I don't have a definition for roots. I have a definition for exponents. So then u prime is going to be 1/2 t to the negative 1/2. Okay? Our v is going to be a plus bt. So then v prime is going to be b. Remember, this, oops, wrong one. This right here defines our independent variable as t. So that implies that this a and this b are just real numbers that we don't know yet. Right? They're just some number out there. Could be 5, could be -7, could be pi, could be e divided by 16. We don't know. It's just some number that hasn't been found yet. So then the derivative of that, well, the derivative of a constant value a is just 0, and the derivative of a constant times t is just that constant, so we get that v prime is the letter b, is the constant b. So now putting it all together, what do I get? What do I get? What do I get? What do I get? I get that f prime of t is going to be u times v prime plus v times u prime. Okay, so then f prime of t, u was t to the 1/2. Maybe I'll rewrite that as a root, maybe I won't, times v prime, which was the letter b, plus v, a plus bt, multiplied by u prime, which was 1/2 t to the negative 1/2. Okay, so cleaning things up, I've got b root t plus a over 2 root t plus b over 2 root t. All right, so I'm willing to bet that most people are comfortable with this because that's just that. But I'm also willing to bet there's at least one person out there going, where did this come from? Right? I distributed times a. A times a half is a over 2. And what does t to the negative 1/2 mean? T to the negative 1/2 means a root of t downstairs. So we get a over 2 times that root of t. And then I took that and multiplied it by the second term. B times a half is b over 2. And what's t times t to the negative 1/2? Same base, add the exponents. There's a 1 hiding there, so 1 plus a negative 1/2 would be a positive 1/2, which just means root t. But now I've got two like terms. This is b root t, and this is b over 2 root t. So I need to combine those, and so I get that f prime of t is equal to 3b over 2 root t plus a over 2 root t. And there's my derivative. This is a perfect example of a problem where students will struggle, and their struggle has nothing to do with calculus. Because the only calculus we did was this. Everything else was algebra. Putting things into a formula, that's algebra. Simplifying, that's algebra. And where do most students find their struggles? It wasn't in the calculus, because this calculus, this is algebra. Okay? I'm willing to bet this. If you know anyone who has taken calculus, and if you ask them where did they struggle in calculus, their answer will not be calculus. Their answer will be all of the algebra that they were supposed to know for calculus. All right, we're at 17 minutes, so I'm going to stop this video here. I'll come back for part 2, and we'll take a look at extending the product rule for more than just two things multiplied together. All right, see you for part 2.